Okay, so hello everyone, welcome to the second live interaction session for the course Discrete-time Markov chains and Poisson processes. So whatever questions, doubts you have about the course, you can ask me through chat box and I'll try to answer or solve your doubts to the best of my ability. Yeah, so since I don't see any question right now or any doubt right now, let me just talk a bit about what we have learned in the part of the course that I have taught. So the one important concept that we learned is about stationary distribution. So stationary distribution is basically a probability measure on the state space, right? So it's like a probability mass function where the ith component, so it's basically a vector whose size is the size of the state space. Each component is greater than or equal to 0 and they sum up to 1, so that's a stationary distribution. Before that we also saw what is a stationary measure. So a stationary distribution is a stationary measure such that the components add up to 1. Okay, so stationary distribution, the way you should think about it is like it's like an equilibrium. Fine. So if you start from there, so if the initial distribution is same as the stationary distribution, then you remain there. That's what is the concept of equilibrium, right? If you start from equilibrium, you will remain there forever. So also we know that if you allow any system to propagate for a sufficient amount of time, it will try to move towards the equilibrium. So that's why we have this limiting theorems which says that in the long run the Markov chain is very close to its stationary distribution, correct? So that's the main thing, or that is the way you should think of stationary distribution. Now the main question is whether stationary distribution exists, and if it exists, whether it is unique or not. Well, the situation is much more simpler in the case of finite state Markov chains. So if it is a finite state Markov chain, then stationary distribution always exists, but there can be infinitely many stationary distributions. But in addition, if the Markov chain is also irreducible and finite state, then there exists a unique stationary distribution. So in case of an irreducible finite state Markov chain, the situation is very, very simple, that we have a unique stationary distribution. Fine. But as soon as we move from finite state to infinite state, things become more complicated. So in an infinite state Markov chain, even if the chain is irreducible, there may not exist any stationary distribution. Example, if you look at random walk, either a simple random walk, either a simple symmetric random walk, or even if p is not equal to half, in both the cases, there does not exist a stationary distribution. Fine. So in the infinite state case, there is no, even if the chain is irreducible, it is not guaranteed that a stationary distribution will exist, but if it exists, then it will be unique. In general, if it is an irreducible Markov chain, then there will exist at most one stationary distribution. Fine? Okay. Then we saw this limit theorems. Like one of them said that if you look at this long run proportion of time a chain spends in a particular state, then that is equal. So if we are looking at in the long run what proportion of time the chain spends in state I, then that is equal to the ith component of the stationary distribution. So that was one limiting distribution, limit theorem. Other one was like, now for that we needed one more concept, the concept of aperiodicity. So if the chain is irreducible, so if the chain is also aperiodic, and if say it is irreducible and all states are positive recurrent, then if we know that if it is irreducible and all states are positive recurrent, then there exists a unique stationary distribution. We have seen this theorem. In addition, if it is also aperiodic, then if we look at this quantity that, okay, in the long run, what is the probability that we will find the chain in state I, where I is some particular state, then that is equal to the ith component of the stationary distribution. But for this, aperiodicity is needed. Fine. I gave a counter example in the during the lecture where even if the Markov chain is irreducible and all states are positive recurrent, but if it is not aperiodic, then this limiting result does not hold. Fine. So this was about this stationary distributions of Markov chains. Then we moved on to exponential distributions, which was basically a prerequisite for Poisson processes. We saw various properties of exponential distributions. One of the most important properties of exponential distribution is its memoryless property, or also which is referred to as the Markov property, that, well, one of the ways of saying this is like, for example, say an electrical appliance, its lifetime is, if its lifetime is exponentially distributed, then if, like, say for example, the electrical appliance has been running for a certain amount of time, but you don't know exactly what amount of time, but then suddenly someone asks you, okay, what is the probability or what is the chance that it will run for, say, X units of time more? Then you can simply forget that, okay, the electrical appliance has been running for a certain amount of time. You can very well pretend that, okay, it's just starting, and then what is the probability that it will last for X units of time? So that is what memoryless property or Markov property is, and exponential distribution has this very special property. And then we also saw many other properties, like what is the distribution of minimum of exponentials, that is again exponential, and so on. Fine. And then finally we saw this Poisson process. So Poisson process is basically used to model arrival of events. So it has, so basically at time 0 it starts from 0, so the counter starts from 0. And then two very important properties of Poisson process is what are called stationary and independent increments. So independent increments is basically saying that, okay, if you look at two disjoint intervals, then the number of events or number of arrivals in those two disjoint intervals are independent. That's the meaning of independent increments. And stationary increments means that the number of arrivals in a particular interval depends only on the length of the interval and not exactly where that interval is situated on the timeline. That's what is stationary increment. And another property of a Poisson process, basically the reason why it is called a Poisson process, is if you look at, say, the number of arrivals up to time t, then that has distribution equal to a Poisson lambda t, right? Where if lambda is the rate of the Poisson process, then the number of arrivals in a on an interval 0 to t is Poisson lambda t. That's why it's called a Poisson process. Fine. Then we saw several properties of Poisson processes, like for example, its inter-arrival times are exponential, and again, because of this, the memoryless property of exponential, Poisson process has this Markov property, which again says that you can basically pretend, like suppose you start observing the Poisson process from a particular point of time, you can very well pretend that the Poisson process has started from there, right? So you can assume that from the time from when you are starting to observe the process, that's time zero. Fine. So everything in future and what happened in past, that is, those two are independent. That's what Markov property says, that given the present, the past and the future are independent. Okay. Then we saw this another property, which is conditional arrival times. So suppose you are told that up to time t there has been n arrivals. Then if someone asks you about those under this information, that up to time t there has been n arrivals, and then if someone asks you about when those arrivals happen, then those are distributed according to the order statistics of n IID uniform 0t random variables, right? So that's the theorem about conditional arrival times. Then we saw these two theorems about splitting and merging of two Poisson processes. So if you have two independent Poisson processes and then you merge them, then that is again a Poisson process and the rate just gets added up. So that was one property. And the other, or kind of complementary property, was if you have a Poisson process and then you just split it up, then again those two splitted processes are Poisson processes and they are independent, right? So the second phenomenon is what is called Poisson thinning, fine? And then we ended with this concept of what is called compound Poisson process, which basically is like, say, one situation it models is, suppose like say there are arrivals and like at certain at times distributed according to a Poisson process, and at each such time there are like say some random amount of arrivals. Like for example, you can think of, suppose buses are arriving at a sports venue, and suppose their arrival is according to a Poisson process, and suppose each bus brings say a random amount of spectators, then if you are interested in the number of spectators that has arrived up to time t, that is modeled by what is called Poisson, compound Poisson process. So it basically is sum over I running from 1 to nt, where nt is the Poisson process, and then the summands are xi, where these xi's are independent of nt. So that is compound Poisson process. Again, it is used to model various real life scenarios, and then we saw what will be its mean variance and all those things. Fine. So that in a nutshell what we learned in the part of the course that I taught. So again, if you have any doubts, any questions, you can feel free to ask. So this both discrete time Markov chains as well as Poisson processes are used very much in modeling real life scenarios. So this has both these things have a lot of applications. Like for example, this Markov chains, there is one more generalization of Markov chains, which is called Markov decision processes. So there basically you can control the evolution of the Markov processes by taking actions at discrete time epochs, and then so basically this Markov decision processes are used to model many things. Like for example, these are heavily used in this area called operations research, which is like basically like one application is like the supply chain management or inventory control. All these things use this thing which is called Markov decision process, which is based on discrete time Markov chains. Another place where Markov chains or basically controlled Markov chains find its application is like, and which is very relevant in today's scenario, is this control of epidemics. That is another scenario where Markov chains can be used to model the evolution of an epidemic, or how can you control the epidemic. So that's another scenario. And as I've already said, like wherever you have some kind of arrival process, you can model it using Poisson processes. So these processes are very useful in modeling many real life scenarios. Okay, so I don't see any queries. So maybe I'll wind up the interaction session. Thank you all.